All right, I am live. I'm going to track one. All right, thank you, everybody. Thank you for coming to my presentation. This presentation, of course, is entitled In Space, No One Can Hear You Hack. We're going to talk about getting started in space hacking. Like, what does it take to start doing satellite hacking, interacting with them, grabbing data, etc. So before we get started, let me introduce myself. My name is Kaitlyn Handelman. I work for NTT Data. Now, NTT is sort of like the ATT of Japan. It stands for Nippon Telephone and Telegraph. And my role is a security engineer. Now, what's really interesting is that there's a bit of a secret. I'm not allowed to disclose this everywhere, but for the sake of this presentation making sense, I'm going to tell you right now. Where I actually work most of the time, almost all the time, is at NASA. So yeah, that's why I'm talking about hacking stuff in space. That's why it relates to my job. Most of the time I'm at NASA and I work on projects involving aerospace and yeah. So the reason why it's a bit of a secret, or at least an open secret, I should say, is because I don't want to get targeted. NASA is a government organization. If I put it out on Twitter and stuff, it becomes a big problem. But you can know, it's okay. All right, so why am I doing this? I'm learning too, and I'll get into that in a second. And you remember about 10% of what you're taught and 90% of what you teach. Track one speaker, let's see. Is this better? Is the volume better? Someone said that my volume's low. Waiting for a response. Someone is typing. Let's see. It's low for me too. Okay. How's this? Is this better? All right. Well, this is as loud as the microphone gets, I think. Okay. Hopefully you can hear me. You can turn up your volume. I'm sorry about that. So anyway, before we get started, let me tell you a bit about my background. So before I was working at NTT Data, I was working at, let's see, hold on. Someone has messaged me about my audio. Audio is great, huh? Yeah, my mic is very close. Actually, you can see it's right here. The gain is turned all the way up. I'm not sure why, what's going on with the audio. I'm getting told that the audio is fine. I don't want to spend too much time debugging this. So tip for anyone who might be too quiet, install the extension. Thank you, Demise. Okay, so let me tell you a bit about my background, what I was doing before I was working at NTT Data. So before I was working at NTT Data, I was working with kindergartners. I was a school teacher, actually. And in my spare time, I was doing computers and hacking and stuff. And I actually didn't think I was that good. I mean, compared to the professionals, I mean, oh my gosh, I'm nobody. And also in my spare time, I found a love of astronomy. And so I found myself working with local groups to teach the community about astronomy, what stars were out and constellations were out at the time, how to use telescopes, etc. And I started getting involved in hacking competitions and CTFs. And it turns out I'm actually like pretty good. I didn't even realize it. So I got a call, and it turns out I was just, a perfect fit. And before this presentation, someone asked, how do I get into aerospace? How do I get into this field? And my recommendation to anyone is it really focus on what you're doing outside of work. I mean, it's great that you go to school, and you continue to learn. But what's really going to land you the job in the field that you want is passion that goes, beyond what you're doing. So like I said, in my case, I was doing CTFs. I was doing the CCDC, which is the collegiate cyber defense and cyber penetration testing competitions. So I was pretty busy and just doing things outside, and I didn't really have a goal to get into aerospace, just that my interests and what I was doing outside of work and school just aligned in that way. All right, anyway, so all right, let's talk about getting into space. So in order to get into space, there's something called the rocket equation. Now they tell you, this is a secret. When you give a presentation, don't show equations, but this one is super important. You really need to understand this in order to understand what's going on with rockets. And essentially what this equation says is that, let me get out my annotation tool, is that the initial mass over the final mass. So you start out with mass with fuel and mass without fuel, and a certain efficiency of the rocket. And that gives you the amount of total velocity. So that's what the delta V stands for. It means change in velocity or change in speed. So your total change in speed has to do with your engine efficiency and your fuel. So what does this mean? Basically, this explains why rockets have stages. So what happens is you have a big rocket at the bottom and it uses up a lot of its mass. And then when it's done, it shoves it off. And then you start with the smaller rockets. And this is basically our entire space program. This is rocket science distilled into one equation. And if you're wondering, if anyone says, "Oh, it's rocket science, it's so hard," no, this is rocket science. This is all you're dealing with mostly. I mean, there's very mechanical and engineering stuff you have to deal with, but the main thing you're dealing with is this equation. Let me figure out how to get rid of annotations. Clear all drawings. Okay. Now let's go on. Mouse. Okay. So let's talk about a few important rocketry terms. Yes, you are. Kato Potato says yes. We learned rocket science. You did. That was it. That was rocket science 101. You are now ready to start building rockets. Everything after that is just getting into details. I can't make out a word. What is going on? What if I reduce the gain? Is this better? Yeah, people are saying something's going on with the audio, and I don't know what's going on. I'm getting, let me look in the green room here. You're fine. Audio is great as long as you're facing the mic. Yeah. So I'm being told that the audio is coming in good on through Zoom. So I don't know what's going on your ends. Definitely not my end. So I wish I could do more. Okay. Anyway, so in rocketry terms, if you start getting into a lot of rocketry, you're going to hear these terms come up a lot. The first one we heard about before, delta V, which is just, once again, change in velocity. That's all it is. Can you go from 10 miles per hour to 20 miles per hour? That's 10 miles per hour of delta V. You have something called specific impulse, which once again is just a complicated term meaning engine efficiency. How efficient is it? Do you take a gallon of fuel to go 10 miles per hour faster, or just 1 ounce of fuel? Thrust to weight ratio. Okay, so we do have certain rockets that are really efficient, super efficient, but we don't lift off with them because they're too weak. Think of like ion drives. So one of the important things you're looking at when you're launching, specifically on a planet, is how much thrust you get versus how much your rocket weighs. And that's called the thrust to weight ratio. And we already mentioned this, but staging is when you have a bigger rocket carrying a smaller rocket, carrying a smaller rocket on top of that, and you go in stages. So it's the big rocket that falls away, then you go to the next stage and it's the smaller rocket that falls away, and then finally you get to the final stage of the little itty bitty rocket. And of course, we have to talk a little bit about orbits, because that's what we're going to be dealing with when we're talking about hacking satellites. Orbits are almost never perfectly circular. You're going to have they're always going to usually be in like an oval shape like this, like you see on the screen. And the near part of the orbit is called the periapsis. or you might have heard it if it's in relation to Earth, the perigee. Likewise, the far side of the orbit is called the apoapsis or the apogee. And many of you who are into computers may have heard that term before, because a big software developer back in the early 90s was, of course, Apogee. And their logo was a rocket in high orbit. And of course, a lot of orbits, go straight across the equator, but usually they don't. Usually they're at some sort of incline. And we call that the angle of inclination. And when a satellite passes over the equator, we call that the ascending node. All right, 6 words you never want to hear to say at NASA. It works in Kerbal Space Program. So I have a confession. What really got me interested in rocketry in the first place is, of course, Kerbal Space Program. And I'm one of the few people at NASA who got in primarily through a extensive use of that program. Let's see. Let's talk a little. All right. So now we have the basic understanding of how orbits work. Let's talk a little bit about cybersecurity in space. And here we have a diagram of a satellite, and we can see it's made up of a lot of different components. Hint, hint, a lot of these have cybersecurity flaws. You have antennas connected to SDRs, connected to a bunch of computers, connected on a network. I mean, it can be a mess, even on a single satellite. All right, so what does a communication process with a satellite look like? Well, it starts off with your normal everyday TCP/IP data stream that you're used to all the time. So you have a flight control station on the ground, and then there's some sort of, usually a cryptographic process that the data will go through before being sent. If I can get my tools out, not Spotlight, Draw, here we go. So we start with the flight control station, and then there's some sort of cryptographic process. And then it goes through an SDR. What's an SDR? It's a software-defined radio. We're going to talk a lot about those in this presentation. And then, of course, it gets sent from the SDR to the antenna. From the antenna, then we go to the space vehicle antenna, another software-defined radio on the space vehicle. And then we undo the crypto, go through some sort of data handler on the device, on the space vehicle, and then finally to the flight computer. And that's, once again, it gets sent back into TCP/IP data. So in a lot of ways, the communication on board the satellite and on board the ground station is very similar to your Wi-Fi that you're very used to. And in fact, Wi-Fi uses its own software-defined radios as well. Anyway, next slide. So let's look a little bit closer at the bus on the space vehicle. What's going on? So you have the antenna. That once again goes to the SDR. That goes to the data handler. Now, normally, the developers of the space vehicles are not complete, noobs to security. So they split things up. So you have the flight computer, which controls everything from how the spacecraft operates. So you have the flight controller will control something called a torque rod, which is essentially magnets. If you're in low Earth orbit and you want to rotate your spacecraft, you can use something called a torque rod, which will align itself with Earth's magnetic field, and you essentially get free rotation out of it. Pretty cool stuff. Of course, if you are outside of Earth's orbit, or low Earth orbit, I should say, then you will use something called a flywheel. Now, a flywheel is the same thing in this case as a gyroscope. People who are familiar with flywheels in terms of gearing know that it's an energy storage system. But when you're talking about space vehicles, the flywheels are essentially used for rotating. If you rotate a wheel clockwise, your spacecraft will turn counterclockwise. So you can use that to rotate the spacecraft essentially for free. So rotational turning of your spacecraft can be done without expending fuel. But of course, sometimes you do need to expend fuel, especially if your flywheels, for example, get saturated, which happens very often. So in that case, if your flywheels get saturated or you need to move it or nudge your spacecraft in some way, you can use something called the reaction control system. And that is essentially usually some sort of rocket fuel that does not require hydrogen or oxygen. It's usually something called a monopropellant. So it's something like hydrazine. And the reason why you would use something like hydrazine in space is because you cannot have failures. When things go wrong in space, they stay wrong. You can't go up and fix things. So yeah, RCS systems generally tend to use a monopropellant. But of course, sometimes you have thrusters as well. If you are sending out something like a probe to Pluto, where you really need it to have like an ion drive or ion thruster, you might have that as well connected to the flight computer. And these are all just for movement, and that is completely separate from the payload, because you do not want what is happening on your sensors, on your cameras, on your ion detection systems to affect how the space vehicle is moving. So you have a split. And so the sensors are usually on a separate bus than the rest of the systems on a space vehicle. Yeah, now you want to play curveball. Yes, do. Like I said, that's how I got working with NASA. Lots of Kerbal Space Program, definitely. Yeah, NASA's gonna have some hard times ahead with me in there. Anyway, so there are different types of space vehicles, basically where they and we define them based on where they are in orbit. So the most common type of space vehicle you're going to deal with are called low Earth orbit vehicles. And these are things like Starlink, which orbit just above the atmosphere. In fact, they scrape the atmosphere very on purpose, because one of the ways that we can get spacecraft down is through friction with the atmosphere over time. And so if it goes too high, it won't scrape the atmosphere. So we want, the low Earth orbits to do that. And then, of course, we have medium Earth orbits, which are sort of in between kind of orbits. Like they're not scraping the atmosphere, but they're not too far off. We use that for GPS. We have geostationary orbits, which just means that the orbit takes 24 hours. So the further out your orbit is, the longer it takes. And if you put it out at a very specific distance, it'll take 24 hours. So the space vehicle will look like it's in the same place in the sky all year round. And of course, after that, we have deep space probes. And this is for things like Voyager 1 and 2, Mars, etc. Anything beyond geostationary orbit, including the moon, is considered deep space. So what can possibly go wrong? Yes, a lot of things. Everything goes wrong in space. You have radiation frying the electronics all the time, temperature swings going between 300 degrees Celsius and negative 200 degrees Celsius, whatever. I'm just throwing things out. Collisions, Kessler syndrome, if you know what that is, where space vehicles start hitting each other and create more debris and more debris. Lacking of testing because it's too expensive. Launch vibrations can destroy your vehicle, as well as launch explosions. That happens a lot. Sometimes your solar panels fail to deploy. Sometimes your spacecraft just tumbles. You can't get control of it. Power, deorbit. There's also the anomaly. This is something I learned very recently. There is an anomaly on Earth, or I should say above Earth, where there's a place above South America, this area right here, where spacecraft tend to die. It's called the South Atlantic Anomaly. Basically a bunch of electromagnetic interference kind of streams in that area and it kills spacecraft. Sort of like the Bermuda Triangle, and it's absolutely real. So how do we do cybersecurity in space? And this is what we're really after. How do we secure our stuff? So unlike ground computers, cyber attacks, are not the primary threat to operation. So, like an AWS server, it's going to be up pretty much all the time. You can kind of assume that unless a hacker takes it down. But in a space vehicle, it's just going to get attacked by meteorites and things are going to fail and you can't replace it and things are going to die and you need ways to get access to the system. So it's not like you can prioritize cybersecurity above everything else. And also anti-malware software and other defenses we would use on the ground are just impractical. I mean, not only because of the architectural difference, but because there's, hard power and resource usage limits. A lot of these spacecrafts are just working on trickles of power, and you don't really want that power running, anti-malware software when you need to get data back to the ground. So you really need your spacecraft to be designed to be robust and have everything isolated from each other. So your sensors should not be able to affect your ion drive and so forth. And many spacecraft, and this is a known fault, and I'm going to tell you, like, this is how you hack into stuff in space. All spacecraft have this fault. If you want to get past the encryption on all spacecraft, make sure that the spacecraft or space vehicle cannot communicate with the ground. In that case, the space vehicle will assume there's something wrong with the encryption and fall back to an unencrypted mode. This works on any space-based satellite, regardless of country. This is a known flaw. This is nothing new, but this is the state of cybersecurity in space right now. So what can a threat actor do with a spacecraft? This is my favorite attack. They can tell the payload to use all the power. So essentially they set up a startup routine where they're like, take all the pictures, take every setting, start running the drill or whatever's on the space vehicle. And then so the space vehicle starts using all the equipment, and then it drains all the power, shuts down, and then it starts up again and starts using all the equipment, runs out of power, shuts down, denial of service. And that's kind of the common attack that we've seen so far. You can compromise the software-defined radio and change the frequencies. You can interfere with the navigation on the space vehicle or mess up the thrust. You can permanently disable communications if you somehow mess up the circuit to the software-defined radio. You can permanently disable ground comms, or you can just jam the communications. And of course, cybersecurity begins on the ground. Someone can interfere or steal with the design. A supply chain attack. You can poison the test data, so you think your spacecraft is going to do well when it's not. You can take over a ground station and suddenly get control of the spacecraft. And you can take over, third-party consumer data, install malware in the bootloader of the machine. There's lots of stuff you can do to a space vehicle if you get access to it. So, but what can you do to defend the space vehicle, knowing that all these bad things can happen? One of the most important things is to have watchdog scripts and programs. So you really want to have sanity checks. You want to make sure that everything is behaving as expected. If something is going wrong, you want your space vehicle to go into like some sort of safety mode or require some command from the ground to continue. You also want gold copies aboard. If something goes wrong with an update, if a bad actor installs malware on the machine, you want to be able to fall back to a good version of the software. You want fallback encryption so that if something goes wrong with the encryption, like the attackers upload a new key, you want to be able to fall back to an encryption that's not entirely unencrypted, but you have the keys that you can use with it. You want, of course, you want to limit the amount of resources that your system can use at any given time. So if you realize that you're going to run out of battery power soon, just have the systems turn off the cameras, have it turn off the lasers or whatever is on there. Lasers in space, by the way, is awesome. And you want to, of course, isolate all the buses and resources from each other, because if an attacker gets access to the computer on board the camera, you don't want them getting access to the thrusters or even the other systems for doing scientific research. So let's hack some satellites, everyone. How hard could this be? And so remember I mentioned we're going to talk a lot about software-defined radios. Well, yeah, that's basically the main thing you need to hack satellites nowadays is a $20 software-defined radio dongle. It looks like this. Uh, and you can use that to essentially get into a lot of satellites, or at least download their data and start playing around with them. And by the way, do play around with them. Space is for everybody, including the satellites that's put up there by the governments. A lot of them are not encrypted, like they do not encrypt the data coming down specifically for you to play with. I mean, I really want to encourage everyone to spread out their space legs. Okay, so let's talk a little bit about radio waves and light polarization, because that's going to be a big thing when you are trying to receive data from satellites. So many of you may know of polarized sunglasses, or maybe you worked with LCD systems like the displays, and you know a little bit about horizontal and vertical light polarization. And of course, that applies to radio waves as well, because radio waves are light. And so if you have, for example, if you look at professionally installed TV antennas, you'll notice that all the arrays here are horizontal to the ground. And that's because traditionally, TV signals are sent using horizontal polarization. And so when you are receiving a signal, either on the ground or from space, you want to make sure that your antenna system has the same polarization. Now, of course, the problem, though, is that horizontal and vertical make a lot of sense on the ground. It does not make a whole lot of sense in space, where it's very hard to define vertical and horizontal. So a lot of spacecraft instead use circular polarization, which basically means that the light either kind of goes in a left-handed corkscrew or a right-handed corkscrew. And so in order to receive these signals, oftentimes you'll have to make something like this. And this is what I made. It's a quadrilateral quadrilateral antenna. Basically, it's a bunch of wires that are kind of going around in around and around and around kind of the base, around the center pole like that, and it will receive circularized polarized signals from weather satellites. Let me clear all drawings. Okay. So what can we do? What can we do? Let's start grabbing data from satellites. So when people start, I always say start with NOAA 15, NOAA 18, and NOAA 19. Those 3 satellites pass overhead. Usually one of them or 2 of them are going to pass like once or twice a week. So you go online, and I'll show how to do this later, how to go online and do this. But you can figure out when they're passing overhead and wait outside for their signal. And oh yeah, here's the quadrilateral helicoidal calculator that I used to design the antenna, and how to wire it. How I made the wiring. All right. Anyway, actually back to the target. Right. So we're going to get those. We're going to attack 137.1 to 137.9 megahertz. So that's about 137.5. So right. So we're designing our antenna around that. Let's before we actually grab those signals, let's talk a little bit about how data is transferred over radio waves. So you may have heard about AM radio. In fact, I'm almost certain you've heard that term, AM radio, or amplitude modulation. What does that mean? Well, when you send out a wave, let's say, I don't know, 100 kilohertz, it goes up and down, and you can encode data based on how, quote unquote, loudly or how brightly the signal is coming out. Because we're talking about light, right? So if you make it really dim and then bright again, and then dim and then bright, you can encode, binary data. And that's called amplitude modulation. Frequency modulation is one that you likely have heard about again. It's more common than AM in a lot of ways. And basically what it does is that instead of encoding based on how loud or how bright the signal is, it encodes the data based on frequency shifting. So if you can imagine, if you want to send like a 1 or a 0, you could shift the frequency between 100 kilohertz and 102 kilohertz or something, and you can switch between them to send data. And that's called frequency modulation. And there's another one that's a little less known, but super important. Whenever you're working with binary data, working with computers, phase modulation is going to prop up somewhere. And basically what phase modulation does is it encodes data based on the phase of the waves. So if you have a sine wave, it goes up and down and up and down. And if you record where that phase is, over time, you can encode ones and zeros. And actually, this is almost always, I've never seen a digital device that uses radio waves that does not use phase modulation in some way. So I know this is probably the hardest one to understand, but it is the most important. So when we're getting NOAA 15, 18, 19, we're actually receiving a analog signal, so not digital, and it uses something called automatic picture transmission, which is if you've heard of like slow scan TV, where you have an audio signal contain visual data, that's exactly what's going on. You have a regular FM data signal, an FM audio signal containing an analog image that you can decode. So you take out your antenna, you take out your $20 antenna. You take out your $20 SDR dongle. You go to the hardware store. You make a QFH like this. You make one of those, and that's going to cost you, I don't know, $50 at most, probably less. Probably can do it even if you scrap it. Maybe you can do it for like another $20. Go outside, just record the frequency of the NOAA satellite passing overhead, and you'll hear it. It sounds like tick, 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 tick. And you can then decode an image. And this is an actual image that I decoded overhead. It's always going to be in black and white. And the image quality isn't that great. But you are interacting with a space satellite going overhead. You're tracking it. You're grabbing the data. You're decoding the data. And you're all doing this with hardware that is dirt cheap. You're going to the hardware store. You're using a $20 dongle, USB dongle, and you're interacting with stuff in space. I mean, how cool is that? And by the way, before I forget, I'm not going into the details of what software to decode, because there's let me stop sharing here. I'm going to switch sharing to my browser. Here we go. And I'll link this into the chat here. If you go to samsclass.info, by the way, Sam Bound is I'm Sam Bound's protege. He's my mentor. So we work together on a lot of this stuff. But there's a bunch of projects here about how to do this stuff. And so the first project here is about decoding automatic picture transmission signals. And if you click this link, you go to samsclass.info/space, you can practice decoding APT signals. So you can download an APT signal and decode it, and find a CTF flag. And like I said, that this goes over the software you use. I personally use this NOAA APT software, but there's other software you can use to decode it. Anyway, stop share. I'm going to go back to the slides. Share screen, slides. All right. So yeah, now we've gotten started. Okay, I did a wonderful. Yes. Someone mentioned they did a workshop with Sam. Sam is absolutely fantastic. I love him to pieces. He's a great person. Anyway, so we use an SDR, software-defined radio, to get a satellite signal. How does a software-defined radio work? Because this is something that confused me a lot when I started working with software-defined radios. So when you work with, when you open something like SDR Sharp, which is a very popular software-defined radio receiver program, you'll get something, you'll record something called IQ data. And what is IQ data? What's going on? Well, it turns out that if you're trying to, for example, grab a 137.5 megahertz signal over USB directly, that's not going to work. USB does not operate that fast. You cannot just pump a 135 megahertz signal through a USB cable. That's not going to work. So what you have to do is you have to sort of down convert it. And the way you do that is you multiply. Let me explain what these symbols mean. You multiply the incoming signal. This is multiply. You multiply the signal coming in from the antenna with a sine wave or a cosine. And what you get is a frequency that is both lower than the input and a frequency that's higher than the input. Now, all we care about is a frequency that's lower than the input. So we use a low pass filter to get rid of all the high frequency stuff that we don't want. And so that way we can turn a high frequency signal into a low frequency signal. And so if you are grabbing a 100 megahertz signal and you multiply it with a 99 megahertz signal, 99 megahertz sine wave, you will get you can get a 1 megahertz signal out. Unfortunately, this is kind of lossy. So people who are much smarter than me came up with the idea of IQ, which means in phase and quadrature. Basically, what you do is you take the input of the antenna and you take it through the amplifier, and then it splits. You go through a cosine for the in phase and a sine wave for the quadrature. And you do the same thing again, low pass filter, analog to digital converter, you get the in phase. Once again, low pass filter, analog to digital converter, you get the quadrature. And that's where the IQ comes from. And when you combine these two signals together, you can recreate the original high frequency wave using something that's almost comparable to like sound audio frequencies. And this is how all your digital devices work. Your Wi-Fi, your $20 SDR, they are all doing this IQ transformation. So that's what you're doing when you're recording on a SDR program and you see this like record IQ. That's what's going on. That's why you're not just recording a straight 200 megahertz sine wave or 200 megahertz input. You're doing all these calculations first to down convert the signal to something that can pass through a USB cable. Let's clear the markings again. So right, so in phase quadrature just means 90 degrees of phase difference. Okay, so let's talk about encoding digital data using this. Remember when I said PM, like super important for digital data? Well, you can plot IQ in like a 2D graph. Let me once again pull up my drawing. So you can plot it like this. So you have Q vertical and I horizontal. And so when you receive a signal, you can start plotting what you're getting on this sort of IQ circly doodad, right? So if you have a Q of 0.45 and an I of 0.45, it goes here. If you have a I of negative 0.45 and a Q of 0.5, you get something up here. And so you can sort of plot around these. You can plot the points that you're receiving on this on the circle, and it really represents the phase that you're in. And so we can use this to encode digital data using phase modulation very simply. Let me clear drawings again. All right, so how does this work? So let's say you receive a signal and it's in the top right corner. You might decode that as 1, 1. If it's in the bottom left, 2 zeros, so on and so forth. And this is called actually Quadrature Phase Shift Keyring, QPSK. That is very popular when encoding digital data. Your Wi-Fi uses this often. And of course, your satellites use this as well as a simpler version called BPSK, which is bi phase shift keyring, which is just two sides. You just go back and forth between both sides. But yeah, QPSK, very popular. And that's how you encode a lot of digital data. Let me clear drawings again. All right. And you can actually, you can view QPSK data in SDR Sharp, which is once again, a popular program for grabbing SDR data from your SDR dongle. You'll see it down here in the bottom left-hand corner using something called Meteor Demodulator. And we're going to talk about the Meteor satellites in a second because they do use QPSK. And you can see the demodulation down below here. And you can see how the points are kind of coming up in these quadrants, very particularly in these quadrants. Clear all drawings again. So now that we have the tools and understanding of collecting digital data, we can use it to start decoding digital transmissions, which is like, all or nothing. So here's an example of one I did. Once again, overhead, I live in California, as you can tell. Here's the coastline of California. When it's exactly overhead, the quadrilateral antenna doesn't work too well, which is why there's a big gap here. But you do get color images of sorts when you're using digital reception. But you also get higher res images. And once again, decoding these is all on the specifics of how to decode this is in the website, the samsclass.info/space. And so let's talk a bit more about, since we're on the topic, about QPSK and QAM. So normally satellites are going to be using, like I said, the QPSK or just back and forth type modulation, the BPSK, because there's a lot of interference, they're far away, stuff can go wrong. However, your Wi-Fi is usually much closer. And so you can add amplitude modulation to your phase modulation, and you get something called Quadrature amplitude modulation. In which case, what you do is you look at your phase, which is going to be somewhere like, let's say we get a signal that is, I'm going to change my color here, that is in this quadrant down here. Now, if we have a strong signal coming in, it's going to go all the way out to here, all the way out to the end. If it's a weak signal, meaning we're doing some amplitude modulation, it will only go out to here. So now in a single quadrant, we can start encoding 4 bits at a time, or sorry, four different types of, nibbles, I should say. So you can start encoding much more data per wave. But of course, this just requires a lot closer of or a lot clearer of a signal. And this is why when you get Wi-Fi, for example, if you're far away from your router, your speeds will slow down because it will convert from something like QAM to something like QPSK to BPSK and so forth to try to get the data through. But yeah, if you get a clearer signal, you can start encoding more and more data into your signal. Clear all drawings again. All right. So yeah, all right, so we were looking at low Earth orbit satellites. QAM, someone writes, QAM also is what cable modems use. Yes. So like I said, anytime you're using digital devices, you're going to come up with these terms, phase modulation, QAM, etc. So GOES is another good place to start. And so once you've done the APT, automatic picture transmission on the NOAA satellites, once you've done Meteor, you can start going off and start looking at geostationary satellites. And these are awesome because remember what I said? If a geostationary satellite orbits once every 24 hours, so it always looks like they're in the same place in the sky. So after a while, you're going to get kind of bored of planning out your days when NOAA is going to pass overhead. When you start going to the geostationary satellites, what you need to do is just point there at any time you want and grab data. And you're going to need, unfortunately, a beefier antenna. You're going to need a dish. And a lot of people use these little Wi-Fi dishes, and that's what I did. I modified a 2.4 gigahertz Wi-Fi dish to connect at 1.7 gigahertz, which is what the GOES satellites uses. But you get these full disk images from geostationary orbit, and they are absolutely fantastic. And you can get them anytime you want. Anytime. They always look like they're in the same place in the sky, like I said. Of course, you know, taking pictures in space is fun, but we can get into a lot more trouble. There's something called Iridium, the Iridium satellite network. Iridium was put up in the 90s, and it was it's a satellite phone network. So if you're on a boat and you need phone communication, texting anywhere, you know, cell phone won't do. You get an Iridium phone. So this was put up in the 90s, and their idea of cybersecurity back then was, it is so complicated and so advanced, no hacker will ever be able to defeat the system. And it turns out, of course, it is now 2021. You can go to the store, buy a $20 SDR dongle, a $5 GPS antenna, which works on a similar frequency to Iridium, and you can start intercepting people's phone calls. These are all unencrypted. I'm not going to go into the details of how to do this, but it is possible. And if you're interested, I would definitely check it out. Iridium, the Iridium satellite network. Yeah, so to finish, yeah, we're getting close to ending. So I do want to talk a little bit about the deep space network. So on Earth, of course, we have the internet. And in space, we have the Deep Space Network, which consists of 3 sites on Earth that are 120 degrees apart, that look out all across, you know, the solar system and beyond to grab deep space data, including, like, for example, the space landing. Or sorry, the moon landing, not the space landing, the moon landing. And the way it works is it uses something called delay or disruption tolerant networking, which means that it's sort of like another version of TCP IP. It's that kind of layer type stuff, but it basically means that if you can't get the data down, like something in between will hold on to the data and then send it back. And you have these giant networks of things around Mars and Earth and stuff. And you can actually set up a DTN network at home. And once again, samsclass.info/space. And you can absolutely start grabbing stuff off the Deep Space Network at home. There's a link here for UHF Satcom with a bunch of information about that. If you are looking to get into space engineering, looking at how to attack, you know, space vehicles, knowing how to program FPGAs is very important, because a lot of space vehicles use custom hardware, and things like the SDRs are often connected to FPGAs to perform the encryption. So definitely learn some FPGA, you know, Verilog type or VHDL programming if you're interested in getting into space hacking. Operating systems in space. So as you may have guessed, we do not run Windows or Linux usually, with rare exception, on our spacecraft. Usually we run something called a real-time operating system. And usually it's Wind River VxWorks is the operating system you'll find on spacecraft. Now, getting this operating system is really hard. So I would recommend, if you want to get into real-time operating systems, check out FreeRTOS. It's free open source. You can download it. You can actually run it on top of Windows. As far as other open source software you can check out, there's Yamix Mission Control, which is the mission control software used at, you know, NASA, as well as OpenMCT, once again, mission control software hosted and developed by and used at NASA. And of course, the core flight system, which is the software that is put on all spacecraft. If you want to get into space hacking, go through this GitHub repository, learn the ins and outs of this. All the spacecraft run this software pretty much. And yeah, let's talk about some current going-ons. Right now, I'm actually working on a Azimuth elevation rotator. which was based on this guy, WB0OEW. By the way, get a ham radio license if you are interested in space hacking and radio hacking. Ham licenses are your best friend. Anyway, he developed an Azimuth elevation rotator, which is important because when you're dealing with satellites that are moving overhead, sometimes you have to track them. And they get expensive. Anyway, so I'm working on that right now. The other big thing, of course, in hacking news is that the Falcon 9 video from the rockets got decoded, much to SpaceX's chagrin. Unfortunately, as this person points out, all the signals are now being encrypted, but so fun's over. But yeah, tons of stuff to be done with space hacking. And it's just so fun. And I just want to get everyone encouraged and get started. And I hope this helps. Anyway, any questions? Arden writes, I've been ruminating about getting a ham license. One of these days I will actually follow through. Yes, absolutely. The thing about space hacking is that most space vehicles and stuff you'll be hacking work on VHF or UHF. And so all you need is a technician's license to do pretty much all the space hacking you want. And a lot of space vehicles are amateur and will actually encourage you to connect to using your UHF or VHF ham radio equipment. What do you suggest the best place to get an SDR? As much as I disagree with Amazon's policies and their business practices at times, I do have to recommend going onto Amazon, and I'll show you what I would recommend as a first SDR. So if you go to Amazon, SDR blog V3, I think it is. Here it is. Get one of these. These for me have been some of the best. $20. This is actually $27, and usually this is a bit, yeah. You can usually get these with antennas for that price, but this has been probably my favorite $20 SDR. I use this probably more than a lot of the $200 or $300 SDRs that I have. In Canada, so Demise says in Canada, it's basically just your name that gets in a database. You don't have to list your address. That's good. Yeah. So when you get a ham license, say goodbye to your privacy. Your address gets put in a database, and anyone who wants to know where you live can look you up. If I tell you my call sign, yeah. So in Canada, apparently they solved that. But in America, yeah, if you get a ham license, yeah, if you want to know where I live, it's 610 East Waddell Drive, apartment 454, Sunnyvale, California. I can't hide that. You can just go on the FCC website and get that for you. Yes, RTL SDRs are receive only. If you want to do transmit, you'll have to get something like a Pluto SDR or a Hack RF. Those are significantly more expensive. And the best thing to do if you're trying to connect to a space, something in space, is to use something like a HT, so a handy talkie, to essentially send out your signals. Arden says, thank you for the awesome talk. Well, thank you for having me. I'm always happy to talk about space. Space is my passion. Hacking is my space passion. So yes. ULS is a wonderful thing when you're interested in privacy, indeed. Yeah, so anyway, I just want to encourage you, like I said, space is for everyone. If you're interested in getting into aerospace or doing space hacking, it's really not as prohibitive as you might think. $20 SDR, $20 antenna, go out there, start receiving signals. Any thoughts on Hackasat? Yes, so Hackasat is absolutely awesome. I've done all their challenges. It's a lot of fun. It's not necessarily the most realistic challenges that they put up, but I'm definitely happy that we're doing this. Like I said, the state of cybersecurity in in space is abysmal. You know, we put up stuff in space in the 90s. It's still up there. We can't upgrade it. We can't do anything about it. You know, you can listen to people's phone calls. I mean, it's so bad. And you know, no one was even thinking about cybersecurity at the time. So I'm glad we're getting some attention and people are learning about this awesome subject. Yeah, so you can actually go and look at all the presentations made for Hackasat. You can download the VMs for Hackasat. You know, do some of the challenges. In fact, I'm really actually surprised that some of the challenges were kind of on the easy side, and some of the winners didn't do it. Maybe it was a time constraint thing. I don't know, but it just shows you that, you know, there's a lot of work to be done in terms of getting people up to speed on, you know, on hacking in space. But like I said, a lot of stuff in space is intentionally unencrypted for you to use and for you to explore. So please do. It's there for you, including the International Space Station. If you didn't know this, the International Space Station has amateur radios on board, and you can contact them. If you have an amateur radio set up, you can contact them, and you can bounce signals off the International Space Station at times to reach other people. I mean, it is super, super awesome. So absolutely. I just checked the radio bad. Tipo Baofeng. Yes. Yeah. I mean, I'm not a radio snob. If you can get a Baofeng and that works for you, I mean, all the more power to you. In fact, the UV5R Baofeng is easily one of the most hackable handy talkies there is. If you want to turn that thing into like an APRS transceiver, I mean, you're good. You're golden. All right. Yeah, 5R is like, yeah, UV5R is only like $35, says Grimby. Absolutely. Yeah, UV5R got a lot of people started. Yeah, absolutely. I have nothing but respect for people that start off with the UV5R. I mean, there are some radio snobs that, you know, it's like, that's a $35 radio. Why aren't you buying a $2,000 radio or whatever? Well, one, not everyone has $2,000 to spare. And two, I mean, like, it's awesome. UV5R is actually a good radio. Now, granted, I should point out that the UV5R apparently has some spurious transmissions that make it non-FCC compliant, but I mean, whatever. And whatever gets you into radio, whatever gets you into, you know, ham radio hacking and stuff, it's all good by my book. All right, we're a few minutes over. Okay, so anyway, so we're a few minutes over, so I'm gonna head out. Thank you for attending. And yeah, hack all the planets. Don't stop at Earth. Hack them all.